In the previous lecture, we have seen how to calculate leakage reactance of primary and secondary windings, which are having a same height. So, in this lecture, we will study about leakage reactance of different types of windings, such as interleaved winding and windings of different height, etc., and general winding finally. So, let us go through the lecture now. So, leakage reactance calculations of interleaved windings continued from previous lecture. So, here leakage flux does not contribute to the transfer of energy between high voltage and low voltage circuits in a transformer, and thus it is always desired to have a low leakage flux and low leakage reactance. Even in a shell type transformer, in spite of presence of both windings on the same leg, leakage flux still exists. A leakage flux may be reduced to zero only if both windings are placed at the exact same geometrical position. So, a special configuration known as interleaved winding attempts to do the same. Actually, placing in exact geometrical position is not possible physically. So, the closest one can be chosen. See, one of the methods is to go for interleaved windings. What is interleaved winding? So, this is the interleaved winding. Interleaved winding refers to an arrangement in which the winding coils are wound in the form of a disc with a group of discs for the LV windings stacked alternately with a group of discs for HV windings. Here you can see this is the cross symbol represents the current going into the plane, and dot symbol current coming out of the plane. So, this is cross-sectional view of a transformer winding. Actually, primary and secondary both are there. So, you may assume that cross belongs to primary, or then the dot belongs to secondary. So, this is how cross and dot, this is vertical position, and here this side core will be there. So, core will be there. And then here this is one of the windings. So, here the may be considered as primary, and then again the primary is here at the bottom. So, this is how there is a gap between them, because between primary and secondary the voltage difference will be there. Therefore, there should be certain gap between them, air gap. So, these air gaps. So, you can see. And again here some air gap, but at this position, see, this is half winding you may consider, and two halves means this full winding W2 and again full winding W1. So, initially only half winding, and at the last also only half winding will be there. All others will be W1, W2, etc. alternating. So, why these halves are put here? It is for a certain purpose. You can see how MMF wave becomes a trapezoidal in nature. So, that this is how an interleaved winding is placed or constructed. You can see, so this is these are one W2 can be considered as two halves, W1, W2 by 2 and W2 by 2, two halves. Similarly, one W1 also can be considered as two halves, W1 by 2, W1 by 2. So, with this arrangement, it is possible to eliminate the leakage flux in the vertical direction. So, this is vertical direction, right? This is vertical direction. So, in this direction, if you see all along this one, always you have the number of conductors enclosed will always be having equal number of plus and minuses, or equal number of cross and dots. means equal number of opposite currents. So the total current enclosed is 0. Therefore, magnetomotive force MMF is also 0 vertically at any position. So this is how total vertical MMF has been eliminated completely, but it does not eliminate the horizontal. Now horizontally, if you can see, so this is the winding here. So here all conductors of one polarity are there. So this is MMF must be increasing along this, and then air gap it should remain constant, and then again here opposite current, so it must be decreasing and then going opposite direction like this. So here the MMF in the vertical direction will not be 0. Horizontal direction will not be 0. The vertical direction is 0, but horizontal direction will not be 0. So in this direction or radial direction, we have certain MMF that we will see in the next slide. So here the horizontal MMF we just placed here vertically just for clarification only. So this is now tilted here by 90 degrees. So this is a radial position, actually radial direction. This is radial direction. This is the core here. This is the core, transformer core. So now you can see the here first half that winding, or you may consider this as first half. So this is a cross symbol, and then you can see here the MMF increases linearly across the width W1 by 2. This is W1 by 2, and then it remains constant in the air gap, and then again it decreases, it becomes 0 at the middle portion because total this is W2 is the width, and then goes down, and then like this. So this is how MMF wave, this is complete one cycle of MMF wave. This is one cycle of MMF wave. So here in one cycle you have two W1 by 2s, means one W1, and two W2 by 2s, means one W2 of the width. So one W1 width of primary winding, say, and the another W2 width of secondary winding will be there in one cycle. So a basic unit of interleaved winding configuration is shown in figure. So this is one basic unit you can consider. There are n such units. Assume, let us take, for calculation purpose, if there are n such units, then total width of the primary winding is how much? NW1. Because in each cycle there are W1. Two W1 by 2s are there, so it is W1. So total width in the secondary winding is also NW2. Similarly, so if Ni is the total MMF produced by either primary or secondary, neglecting mutual magnetization. So this is if Ni is the total MMF produced by primary or secondary, then one half winding, how much it will contribute? So NW1 means is the width. NW1 corresponds to Ni. Therefore, W1 corresponds to Ni by N, and W1 by 2 corresponds to Ni by 2N. This Ni by 2N. Similarly, W2 by 2 also corresponds to Ni by 2N. So that's how this peak. So each width W1 by 2 or W2 by 2 corresponds to Ni by 2N. So the height, this height is, because since this is half width, so in this half width, this height, it raises to Ni by 2N, HR if it is H. If it is MMF, you can ignore HR. Now what is HR in this case? HR in this case is the effective width of the winding. So in the width of the winding, I mean in the radial direction. Effective width in the radial direction means this one. So this Rogowski height in this direction. So it has to be similarly found just like the previous case, but it is a little bit different actually. It is not exactly same. HR, you can capital R, right? So this is a little bit different from the HR we calculated. This is actual radial width of the winding, and then a little bit higher will be the Rogowski height HR. Now this is about this one. Now this width, axial width, this width is W1 by 2 and W. Earlier in the previous case, in the last video, you can see W1 is actually radial width we have considered as W1, W2, etc. Now here the W1 is the width of the interleaved winding here. So the air gap must be more or less same as the previous case, because air gap depends on the voltage level, voltage difference between primary and secondary. Therefore, previous case also, in this case also, this width, axial width Wg here, in the previous case it is radial width Wg, are more or less same. So this Rogowski height, you hope you understand. So if you divide MMF by Rogowski height, see Ni by 2n is the MMF, Ni by 2n HR is the H, that is in magnetic field intensity. MMF by Rogowski height, if you divide it by Rogowski height, you will get magnetic field intensity. So in field intensity is also trapezoidal in nature. So this is one cycle. One cycle consists of one full W1 and one full W2. So there are n such units. N such units means how many such a half units, half circles means this is here. This, the energy stored in this is exactly same as the energy stored in this. There is no difference, because H square will come. So even if it is minus, it doesn't matter for us. So the energy stored in this positive trapezoidal period and then the next half cycle is also same. So we can find out now energy stored in this half cycle and multiply it by 2n, because there are n such cycles, so 2n such half cycles. So this is how we will proceed now. So thus for one section, the energy stored in the air gap, so you can see here from in the W1 by 2. So this is Eg half air gap, it is written, sir, air gap, in one air gap. It is not one section here, for one air gap. So in one air gap, because in the air gap it is Ni by 2n HR, and everywhere it is same, all air gaps. So Ni by 2n HR, half mu naught H square into volume. So here again pi d. D is the mean diameter of the winding. So Wg is axial width now, axial air gap width. HR is in radial effective Rogowski width, you can say. So pi d Wg HR corresponds to the volume, and then this is volume, and then this is half mu naught H square. This is energy density per unit volume. So volume into energy density, that's what in one air gap, in one of the air gaps, this is the value. Similarly, energy stored in the windings, we have seen it is W, whatever width, W by 3. So here, since it is W1 by 2, W1 by 2 by 3, it will be W1 by 6. So that is the only difference in this triangular portion of the wave. So the energy stored corresponds to this equation. And similarly, in this portion, the energy stored corresponds to this one. Okay. So this is how energy stored in the windings can be calculated. Now, how many such units are there? This is now, until now, this corresponds to only half cycle, right? So there are 2n such half cycles. Therefore, and assuming this is reasonable, because all windings are exactly same radial width. Therefore, same mean diameter is reasonable assumption. So, d1 is equal to d2 is equal to dg is equal to d. So, that's what is assumed here. So, the next thing is to find out energy. Actually, this has to be integrated and then found. Already we have done in a triangular portion. If you integrate and all, so what is effectively this width will become W1 by whatever is the width is there by 3 it will become. So, here already W1 by 2 is there. So, W1 by 6 it is taken. This is the only difference from air gap calculations. So, that's how we have finally came to this conclusion here. Directly equation is used here. But if you want, you can go back and then do integration similarly the way we have done earlier in the previous video. Now, thus the total energy in the entire system by virtue of leakage flux is given by this E1 plus E2 plus EG, and such 2n half cycles are there. Therefore, this is the total energy, which is equal to half Li square, I square, Li square. So, you are referring to, if I is referred to primary current, so you will get the primary leakage reactance, referred to primary, including secondary plus primary, referred to primary you will get. If you use I as secondary current, then you will get entire leakage reactance, leakage inductance referred to the secondary. So, this is how it will happen. So, here Ni by 2n HR whole square pi d HR into this W1 by 6 plus W1 by 6 plus Wg into 2n is equal to half Li square. Therefore, L is total inductance is given by this. So, L equals to 1 by 2n into mu naught n square pi d by HR W1 by 6 plus W1 by 6 plus Wg. So, the interleaved winding thus leads to a reduction of leakage reactance by 1 by 2n. Of course, assuming that W1, W2 and Wg are of the same order and HR is almost same order. So, if that is the case, then it is reduced by 1 by 2n. So, this is how interleaved winding will reduce the leakage reactance. Next, windings of unequal height. So, in general, the windings can be unequal. HV winding and LV winding may be of different heights. So, this is not interleaved winding. This is only that this is the primary winding. This is the secondary winding. Secondary winding is of lesser height. Here, it is taken like that. So, the current rating of the HV winding is much lower compared to the that of the LV winding. Accordingly, its thickness is less than that of the latter. See, the wire thickness depends on the current actually. Similarly, the height of the two windings need not be same. So, unequal heights of the windings introduces a non-uniformity distortion in MMF profile in the radial direction as well. So, which was not so in the case of equal heights. So, when we considered earlier equal heights, we have taken only MMF in the vertical or axial direction. So, here we have taken like this, right, if you remember, and then going down. So, but in the radial direction, we have neglected because in the radial direction, of course, at the edges it will be, but we have neglected because of Rogowski height, taking Rogowski height to consider that one. So, since the conductor's currents, if the heights are same, the currents included or magnetomotive force included cancels out each other. So, that's how we have taken it as 0 or negligible in the radial direction. Now, here, if the windings are unequal, this introduces a non-uniformity or distortion in the MMF. So, in the method proposed by Rogowski, radial distortion was ignored. Thus, to apply the method, we need to reduce the unequal height case effectively to the case of equal heights. And so, there is a procedure actually. So, by the procedure, simply you see the radial direction and axial direction and plot the MMF. Of course, it is, the resultant MMF is non-linear and all is resultant of these two, two directions. One is axial direction and radial direction. So the flux lines are different, but you can, study these two components, and then total energy can be calculated by summing up the individual energies of these two perpendicular, components. That is, one is radial component and axial component. So we will see radial flux and axial flux, or radial MMF or axial MMF, and then finally total energy can be calculated independently, individually, and then summing up. That is possible. That can be proved theoretically also. So it is done like that here. So you can see this winding. So since here, if you see from this direction, in this direction, only this current is included up to this portion. Which current? The primary current. After this, primary and secondary currents will cancel out each other, and then again you see only primary current at the end of this one. So MMF is simply proportional to current into number of turns, right? So since total winding, so this primary winding will have Ni. N1 I1 is Ni. So N2 I2 is also Ni. So total primary magnetomotive force is Ni and secondary also Ni. So for this complete height, what is the per unit length? It is Ni by H is per unit length. Now since this is taken as A here, A, and this is total width is B, that second winding B, and again it is divided into B1, B2. Let us see what those are, and this is again C. So these are the different widths where in the C portion as well as in the A portion we don't have the secondary winding here. So total Ni ampere turns are within this height B only for secondary winding. So total. So here there are no Ni, and here in this portion also no ampere turns. So obviously the ampere turns must be increasing in space like this and reaching a maximum. And from here, since opposite current has started, this is secondary. Secondary is opposite, therefore it must decrease. So it decreases in the middle, it becomes somewhere around B1, it becomes 0, and then goes to negative, and then reaches its negative peak here, and after that only secondary winding and only primary winding should be there, and the primary winding should bring it back to 0, because this Ni whatever is contributed by the primary winding is, if you consider as positive, this Ni contributed by the secondary winding is negative. So total Ni must be 0. So it must start from 0 and end at the 0. Of course, neglecting that mutual MMF or mutual flux. So this is how the MMF wave in the radial direction should look like. Now there are several unknown things here. What is B1 at which it crosses this one? What is the peak? This peak we can calculate. And then what is B2 and R? So these can be actually calculated from simple known values actually. So here Ni, this total winding is Ni. So winding the Ni per unit, the ampere turns per unit length is simply Ni by H, right? Ni by H, and this width is A. So this height is simply Ni by H into A, because per unit length that is Ni by H, and for a length of A it is Ni by H into A. Similarly here this peak also simply Ni by H into C. Only that you should know A, C, and the other thing is B. B you know. Now from, so once you know this, simply draw a line from this point to this point. Okay. Then you will get exactly where it will intersect with this line, with this horizontal line. So here you can see this is theta, this is also theta. So we will do simple analysis and then find out the relation between these two, B1, B2 and B, etc. Now in the vertical direction again, it is exactly similar to what we have done earlier, vertical direction. So here since widths or heights are unequal, but the MMF is same. MMF, total MMF of primary is always equal to total MMF of secondary. Therefore, within the width W1, so it rises to the peak value Ni. Complete total primary is coming here in the picture, and then it remains in the air gap constant, same value, and then goes down. This is the MMF rate for this one. Now it is in the vertical direction, it is like this. So it is Ni, and this is how radial and axial direction MMF will be. And now for calculation, see here we need for calculation tan theta is same. This angle theta is same, right? Tan theta equals to Ni by h into A, what is this height, divided by B1, and then is equal to Ni by h into C, this height. So Ni by h into, so therefore this gives A by B1 equals to C by B2 equals to A plus C by B1 plus B2. A by B1 is equal to C by B2. Therefore, it is also equal to A plus C by B1 plus B2, which is B1 plus B2 is B. Therefore, A plus C by B. Now, from this B1 can be obtained. B1 is simply AB by A plus C, and B2 is BC by A plus C. So, B1, B2s are obtained. Now, after obtaining this, calculation of total magnetomotive force or total energy stored is easy. Now, while calculating the energy along the radial direction, we need to consider Rogowski height along the radial direction denoted by WR. So, H in this radial direction is equals to MMF by WR. So, the vertical direction it is HR, in this direction WR. So, using that the radial energy stored is simply half mu naught Ni by H into A by WR whole square. This is H square, and then this is the volume, and similarly again this is H square in the other one, and then again this is the volume. Place axial direction, sorry, this is all radial energy. All half circles, half triangles are considered. So just go back. So this you can see, this is one half, this one triangle. This is another triangle. These are half of the big triangle, right? And then this is one half. So total 4 triangular portions are there. And for that, using the same formula as before, just the width C or A or B1, B or B2 becomes by 3, 1 by 3. So all these radial energies are added in this formula. So once obtaining the radial energies, and similarly axial energies also we can obtain exactly in the same fashion, where W1 by 3 plus W12 by 3 plus Wg will be there. So if you simplify the radial component, it will become like this. So total energy will become like this in the unequal case of windings, unequal height of windings. So equating this to half Li square, if I is the primary current, you will get all inductance referred to the primary. If I is the secondary current, then you will get all inductance referred to the secondary. So this is how the leakage reactance will come out to be. Now having done for this unequal heights and then interleaved winding, now the main method of calculation is understood now. Now for an arbitrary winding also we can do. Now here is one example for your assignment purpose. So this is tap changer. Simple tap changing is given here, 50% and then 100%. So here you can assume. So of course percentage can be different. This is one tap. Suppose the transformer is operating with this tap. So what will happen? I will give the clue. Suppose it is operating. This winding is not functional. You can ignore this existence of this winding. And here it is operating like this, secondary. And this is primary. Okay. Now this is primary. Now, so here total MMF is Ni here. Again this is Ni for this portion. So this is vertical direction, it will be like this only. But in the radial direction, here there is no MMF. So you have to, for this one, for this winding. So this winding you can ignore. Only one direction you have. So until this point, the MMF will be simply growing like this linearly. And here these two are at same height. Therefore, at this position it has to become 0. So here the negative slope will start. Okay, maybe much steeper and then become 0 here. So this is of more width, this is of more width, and this is of less width, of course. This is how the MMF wave will be there. So we can calculate and then find out what it is, what is the energy stored and all. So using that you can calculate that. Now for arbitrary winding. So for arbitrary winding, here of width W1 and W2. So see here Wn is given here, Wgn gap, Wn plus 1 and Wgn plus 1 and Wn plus 2, like that. So for arbitrary width also, so here if it is dx, the magnetomotive force at any point is given by f of x is equal to fn minus 1, that is previous value of f, and then plus x by wn, whatever is the total wn, x by wn into fn minus 1. So whatever is there, that this is a triangular linear linear approximation of magnetomotive force. And then therefore h of x is equal to f of x divided by h of r. So that can be calculated. Thus the energy stored is from, this is integration of from 0 to n in En. En means in the winding portion of Wn. The energy stored width Wn is 0 to Wn half mu naught hx square. This is hx. Is a function of x. There is x here, there is x here. So hx square into dv, where dv is pi d into d is the mean diameter into dx is the width and hr is the Rogowski height hr. So this is how it is, and then if you integrate this, you will get this expression, and then simplifying we will get this kind of equation. So this is how the energy stored in width n, width Wn is given by half mu naught pi d by hr Wn by 3 into fn minus 1 square plus fn into fn minus 1 plus fn square. Fn is the MMF of nth stage. So therefore similarly the energy stored in the nth air gap. So air gap also we have to consider. This is Fgn whole square, where Fgn is simply Fn. So this is how the energy stored can be calculated. Once energy stored is calculated, then the total energy must be equated to Li, half Li square, to find out the leakage reactance. So thus if M is the number of windings, P is the number of air gaps, then the total energy associated with the leakage flux is sigma. You can use N is equal to 1 to M and this thing, and then again for air gaps N is equal to 1 to P, this thing. So this is how total energy is found. Once total energy is found, equate that to half Li square to find out the leakage reactance. So this is how, for a general distribution of windings, the leakage flux, leakage reactance can be calculated. Thank you.